Hello friends, today we'll discuss about how to convert the regular expression into a DFA by using a direct method. The book which I have referred for this is Compilers, Principles, Techniques and Tools. These are the steps required for converting a regular expression into a DFA. First of all, we need to construct a syntax tree from the augmented regular expression, that is R hash. Then we need to compute nullable first position, last position and follow position for the syntax tree. Finally, we need to construct a DFA by using dstates and dtrans. These are the rules for computing nullable first position and last position. This is an algorithm again required for converting regular expression into the DFA. And finally, these are the rules required to compute follow position. All these things we'll discuss by taking an example. So let's move on to the example. The regular expression is A or B star A B B. The augmented regular expression for this expression is A or B bracket star dot A dot B dot B dot hash. In this, dot is nothing but concatenation operation and hash symbol is called as the end marker symbol. For this, now we need to construct the syntax tree. You can see there are symbols like A or B in the augmented regular expression. So we'll begin with these symbols. We can see we are having symbols A and B, and let's combine them together with the help of OR operation. So it gives us something like this. Then we need to apply star operation on this expression, which gives us like this. Then we'll apply concatenation A, then concatenation B, then concatenation B, and finally concatenation hash symbol. So the complete syntax tree is something like this. Then whatever the leaf nodes are there, we'll number these leaf nodes starting from left to right. So here it gives us something like this. Let's calculate the first position and last position of these nodes. So to begin with, node A is the leaf node. So the rule says that if a node is a leaf node, then the first position and the last position of the node is the position itself. That means first position of node A is equal to its position, that is 1. Similarly, last position of A is equal to position of that node itself, that is equal to 1. Similarly, we can calculate first position and last position of node B, which will equal to 2 respectively. Then the first position and last position of remaining nodes we can calculate, or we can directly write by using their positions. So it gives us something like this. Moving ahead, we will calculate the first position and last position of the internal nodes now. So to begin with, we will find out the first position of the OR node. For the OR node, the rule says that first position of OR node is equal to first position of C1, that is the first child, union first position of C2, that is the second child. So we know that OR node has got A and B are the children for this particular node. So first position of OR node is equal to first position of A union first position of B. So we can write it is equal to 1 2. Similarly, we can calculate last position of OR node, which is equal to, again as per the rule, last position of C1 union last position of C2. So it is again equal to 1 2. Then let's calculate the first position and last position of this star node. It says that first position of star node is equal to first position of C1, that is the only child of this star node. In our example, R is the only child for this star node. So whatever the first position of OR node is there will be the first position of the star node. Similarly, last position of the star node will be equal to last position of the OR node, that is equal to 1 2. Moving ahead, the concatenation operation, the rule for first position of concatenation operation says that if C1 is nullable node, C1 means the star node, if it is nullable, because this is the first child of the concatenation node, if it is the nullable node, then first position of this concatenation node will be equal to first position of the first child union first position of the second child. In this case we can see star node is nullable node, and that's why first position of concatenation node will be equal to first position of star node union first position of A, that is second node, which is equal to 1 2 3. Similarly, last position of the concatenation node will calculate based on the rule which says that if the second child is nullable, then the last position of this concatenation node will be equal to last position of the first child union last position of the second child. But we can see this node A, the second child is not nullable, and that's why the last position of concatenation node will be equal to last position of A, that is 3. Moving ahead, the first position of this concatenation node, again same condition will apply, but we can see now this concatenation node, that is C1, is not the nullable node, and that's why we can write first position of concatenation node is equal to first position of the first child, that is equal to 1 2 3. Similarly, last position we need to again apply the same rule. If the second child is not nullable, then last position of concatenation node will be equal to last position of the second child, that is 4 in our example. Moving further, this concatenation node again we'll see its left child or the first child, it is again not nullable, and that's why we can write the first position of the current concatenation node is equal to first position of the left child or first child, which is equal to 1 2 3. And similarly, the last position of the current concatenation node will depend upon the second child, whether it is nullable or not. In our example, second child, that is B, is not nullable, and that's why last position of the current concatenation node is equal to 5. And finally, the root node, again it is a concatenation node, we will apply the same condition. We can see again the left child is not null, that's why the first position of the current node is equal to first position of its first child, that is equal to 1 2 3. Similarly, we will check the last position. The second child is not nullable, and that's why last position of the root node is equal to last position of the second child, that is hash, which is equal to 6. Right? So this is the complete last position and first position of all the nodes in the syntax tree. Now we will find out the follow position. Follow position is applicable only to concatenation node and the star node. Now let's consider this as the star node. The rule for the star node says that if n is a star node and I is a position in last position of n, then all positions in first position of n are in follow position of I. Let's split this statement. We'll consider the node n is equal to star. Let's find out the last position and first position of this star node. We can easily see from this syntax tree, last position of star is equal to 1 2, which is highlighted in blue color, and the first position of star is equal to 1 2. Now let's consider I. We have to take I from last position. Okay, so to begin with, I is equal to 1. What rule says that if I is a position in the last position of n that we have taken, then all positions in first position of n are in follow position of I. That means if I take I is equal to 1, so follow position of 1, which is equal to first position of star, which is equal to 1 2. So I can write follow position of 1 is equal to 1 2. Now let's consider I is equal to 2. It is same way, follow position of 2 is equal to first position of star, which is equal to 1 2, and that's how we can write here. Moving ahead, next node is concatenation node. For the concatenation node, the rule says that if n is a concatenation node with left child C1 and right child C2, then for every position I in last position of C1, all positions in first position of C2 are in follow position of I. Let's again break this statement. We'll consider node n is equal to concatenation node. Let's find out last position of C1. This is what we require, last position of C1, which is equal to 1 and 2. For this concatenation node, star is the left child, okay, and its last position we need to find out, that is equal to 1 2. Similarly, for the concatenation node, right child or the second child is A, and its first position we need to calculate, so it is first position of C2 is equal to 3. Now we need to consider I, that is from the last position, so we'll take I is equal to 1 initially. So follow position of I, that is follow position of 1, is equal to first position of C2, that is equal to 3. So you can write first position of follow position of 1 is equal to 3. In previous case we have seen it was 1 2, now we have added 3 into that. Similarly, I will be 2 now, so follow position of 2 is equal to first position of C2, that is equal to 3. So you can write follow position of 2 is equal to 3, and previously we have taken 1 2. Moving ahead, again the same rule we'll talk about now. This concatenation node, again we require last position of C1, which is 3, and the first position of C2, which is equal to 4. Now here we'll take I from the last position of C1. So rule says that last position of C1 we have to pick up I, and follow position of 3, that is I, will be equal to first position of C2, that is first position of B, which is equal to 4. So you can write follow position of 3 is equal to 4. Moving to the next concatenation node, here again the same rule is applicable, so we'll calculate the last position of C1. For this concatenation node, C1 is this concatenation node and its last position is 4. So last position of C1 is equal to 4. Similarly, first position of the second child, which is equal to 5. So we can write I is equal to 4. We have to pick up I from the last position of C1. Now we'll take I is equal to 4. So you can say follow position of I, that is follow position of 4, is equal to first position of C2, that is 5. So you can write follow position of 4 is equal to 5. Let's go ahead. Finally, the root node. Again we can see it is concatenation node, so we need to calculate last position of first child. So you can have last position of C1 is equal to 5, and the first position of the second child, so first position of this hash symbol is equal to 6. Now here again we will take I from the last position, I is equal to 5, so follow position of 5 is equal to first position of C2, so it is 6 in our case. So follow position of 5 is equal to 6 we can write. And finally we can see node 6, it does not have any further first position or any further parent, so we can say that follow position of 6 is equal to 5. So this is the complete table of the follow position. This is what we have already constructed. Now this is the algorithm which we have already seen to convert the regular expression into a DFA. So what we'll do, we'll be having a variable called as the D states. We'll initialize it to first position of n0, where n0 is the root of the syntax tree. Now if you go back to the syntax tree, so here here in this case the first position of root node is 1 2 3, so we'll take that 1 2 3 as value of t states. Okay, now in this what we'll be doing is, these are the positions we have to pick up, and out of these positions we have to consider the sigma. What is sigma in our example? It is a and b. Now out of these three positions we'll pick up the positions which are corresponding to a particular sigma or particular input alphabet. You can see from the syntax tree, position 1 and 3 are corresponding to A, and position 2 is corresponding to symbol B. So we'll pick up position 1 and 3 which correspond to A. So here I write position 1 and 3, they correspond to A. So as per algorithm, Q is equal to follow position of 1 union follow position of 3. Where you will pick up follow position? Here is the table. Follow position of 1 is equal to 1 2 3. So we'll write 1 2 3 union follow position of 3. Follow position of 3 is equal to 4. So we'll write down follow position of 3 is equal to 4. Take the union of these, we'll get 1 2 3 4. So this is nothing but the transition we are getting. So we have applied delta of 1 2 3 comma A, which is equal to 1 2 3 4. Similarly we will apply B on this 1 2 3. So B corresponds to position 2. So here it is, 2 corresponds to B. So we'll just take follow position of 2. Follow position of 2 is nothing but 1 2 3. So we'll write down follow position of 2 is equal to 1 2 3. That means delta of 1 2 3 comma B is equal to 1 2 3. Now whatever the new states we have got, we will apply A and B on these new states. We have considered 1 2 3, right? State 1 2 3. We'll take now the new state, that is 1 2 3 4. On this state we'll apply A and B. So moving ahead, on this 1 2 3 4 I will apply A as well as B. Now when we say we'll apply A and B, what we need to do is, from these positions we need to pick up the positions which are corresponding to this symbol A. We can see position 1 and position 3 are corresponding to symbol A. So we'll take follow position of 1 union follow position of 3. Follow position of 1, it is there in the table, it is 1 2 3 union follow position of 3, it is 4. Write down 4, which is nothing but 1 2 3 4. Now when we apply B, out of these positions 1 2 3 4, we'll check which positions correspond to symbol B. We can see now position 2 and position 4, they correspond to symbol B. So you can write down follow position 2 union follow position 4. Again go back to the table. Follow position of 2 is equal to 1 2 3 and follow position of 4 is equal to 5. So you can write down 1 2 3 5. Now in this transition, what is the new state which you have got? It is 1 2 3 5, because 1 2 3 4 we have already considered. 1 2 3 5 we will consider it now, and again on this state we will apply A and B. It gives me something like this: 1 2 3 5 comma A and delta of 1 2 3 5 comma B. Now in these positions 1 2 3 5, we will see which positions are corresponding to symbol A. Again let's look into the syntax tree. Position 1 and position 3, they correspond to symbol A. So we'll take follow position of 1 union follow position of 3, which gives us again 1 2 3 4. Then you can see symbol B, or the position 2 corresponds to symbol B and position 5 corresponds to symbol B. So we'll take follow position of 2 union follow position of 5. Follow position of 2 from the table we can see it is 1 2 3, and follow position of 5 which is equal to 6. So we'll take their union, which gives us 1 2 3 6. Now in these transitions we can see 1 2 3 6 is the new state which you have got. On this state we'll apply A and B. Let's move on to the next state. So 1 2 3 6, out of these four positions, which positions correspond to A? Again it is 1 and 3, so we'll take follow position of 1 union follow position of 3. Look into the table, it is again same thing, 1 2 3 and 4. Let's take union of these, we'll get 1 2 3 4. And 1 2 3 6, check the positions corresponding to symbol B. Here you can see only position 2 corresponds to symbol B. Position 6 corresponds to symbol hash. Hash is not an input alphabet, so we will not consider that. So you can write only follow position of 2, which is equal to 1 2 3. Now you can see in this transition I don't find any new state. 1 2 3 4 is already considered, and state 1 2 3 is also already considered. Now if we combine all these transitions and we'll write into a table, it gives us something like this. Now we need to decide which state will be the initial state and which states will be the accepting states. The rule says that the first position of root node of the syntax tree will be the initial state. If you remember, the first position of the root node of the syntax tree is equal to 1 2 3, and that's why this state is the initial state. And the accepting states are those containing the position for the end marker symbol, that is hash. Again, if you remember our syntax tree, in that hash symbol is present at the position number 6, and that's why the state which consists of position 6 will be the accepting state. So in our case it is 1 2 3 6, so this state will be an accepting state. From this transition table we can construct a transition diagram, which is like this. This is how we can convert the regular expression into a DFA by using a direct method. Thank you.